Hello, everybody. Welcome to Calculus 1, Day 9. We're doing Section 3 of Chapter 2, one-side limits, but more so we're talking about the epsilon delta proof. What we're going to do here is we're going to prove to show that the limit of f of x as x approaches c is equal to some number L. What that shows is on any curve f of x, the limit value L as the gap here on our x values to go to c, between x and c, the gap here called delta, it's going to go infinitely close to 0. And accordingly, these gaps here on the y-axis, we call that epsilon, and that's going to eventually go to close to 0 as well. So remember we said that it doesn't have to get to c, it just has to approach it. So our first example. Consider the function y equals 2x minus 1 near x equals 4. If we look at that, all we really have to do is plug it in there. We plug in our c value inside there, so we get 2 times 4 minus 1. We get to 7, and that is our limit function. So how close to 4 do we have to get? But that's the whole thing's all about. Okay, so we know that that's going to be in there. So how close to 2 do we have to get? Do we have to have, or if it's less than 4, less than 1? All right, so what we're looking at here is the absolute value of our function, 2x minus 1 minus 7 is equal to some number. We'll say 2. Simplifying this, we get 2x minus 8 so that becomes, we can factor out x minus 4. That's going to be 2. So we have absolute value of x minus 4 is less than 1. We drop the absolute value signs. We get negative 1 is less than x minus 4. Solving for x, we get 3 is less than x is less than 5. So remember, our first one, we said how close to 4 do we have to get? So we're looking at as x gets close to 4, we get x minus 4, it gets close to 0. So with respect to this, since our equation here was x minus 4, we said that this is true, So x minus 4. If we subtract 4, we get negative 1. X minus 4 is 1. So this tells us that x is within 1 unit, plus or minus 1 unit, of x equals 4 to keep the function within the 2 units we looked at earlier. All right, so that's what we're looking at here. Again, the epsilon delta is, if we look at a linear equation, this is our value c, which is equal to 4. Its limit value is 7. But if we go from 3 to 5, and we plug it into our equation, and we'll go from 9 to 5. And as we get closer, our limits approach that. So as our value x approaches c here, and the distance becomes 0, our function approaches our limit, and the difference eventually becomes 0. So this is what we're looking for. As x approaches c, we're trying to show that this little opening here, this delta x, which is delta, it gets smaller and smaller and smaller. All right. Page 2. Definition of a limit. Let some function f of x be defined on an open interval AB and C is an element inside that open interval, and f of C may or may not be defined. Remember, it doesn't have to get to C for it to exist. The limit of our function f of x as x approaches C is equal to L. Yeah, it's written as x approaches C, our function f of x approaches L. This is true if for every epsilon greater than 0, there exists a delta also greater than 0. Instead of, now, there exists, I'm using that symbol, a delta greater than 0, such that our function to L is less than epsilon when our x approaches C goes close to 0. So here's our C Here's our x1 and x2. So this is C minus delta. This is C plus delta. This is our delta. And that corresponds to some value L. This is L minus epsilon. This is L plus epsilon. Those values are the epsilon. So let's look at example 2. Show that the limit as x approaches 1 of 5x minus 3 equals 2. Remember, this is as x approaches c, so we know our c value is equal to 1. Our f of x is 5x minus 3. Our limit is 2. So for any epsilon greater than 0, we find a delta greater than 0 such that if x does not equal to 1 and x is within delta of c equals 1 or x equals 1, which is our c value, we get x minus 1 is delta. We also know that f of x is within epsilon of L. Here in our case, L equals 2. So we get f of x minus L is less than epsilon. F of x minus 2 is less than epsilon. 5x minus 3 minus 2 is less than epsilon. That's our function. We get 5x minus 5 is less than epsilon. 5 can be factored out. So we know that our absolute value of 1 is less than epsilon divided by 5. Three. Now we got to put those two together. We have x minus 1 is less than epsilon over 5. And we also have this epsilon over 5 is equal to our delta. Because these are equal, has to be greater than 0. So we're saying that that has to be true. To show this, we have 0 absolute value of x minus 1 is less than epsilon over 5. Gives us our f of x. This is f of x minus L is equal to 5x minus 5, which is equal to 5x minus 1 is equal to 5 epsilon over 5 is equal to epsilon. This shows that L equals 2 is the limit of our function. As x approaches 1, only if we get our functions only if we get these equal for any epsilon and any delta. Epsilon 3, prove A, the limit as x approaches c of k is equal to k, and B, the limit as x approaches c of x is c. Again, given any epsilon greater than 0, we need to find a delta greater than 0, such that f of x minus L is less than epsilon. In this case, k minus k is less than epsilon when x minus c is less than delta. We see that the k minus k is equal to 0. So k minus k is less than epsilon, which is 0 is less than epsilon. Any positive delta. Because it's automatically greater than 0, and delta is automatically greater than 0. All right, let's look at B. Okay. So for B, again, given any epsilon greater than 0, we need to show such that absolute value of f of x minus L is less than epsilon. So it's our function is x minus c. when we see here, if these two are equal, we know that epsilon equals delta. Is true for any epsilon greater than 0. So again, that shows us that limit as of f of x as x approaches c is equal to c for any value x. Page 5. Page 4. All right. Let's look at finding deltas algebraically. For given epsilons. We just saw an exact last two examples. Last two examples we had limit as x approaches 1 of 5x minus 3 equals 2. Limit of k as x approaches c equals k. And now our limit as x approaches c of x is equal to c. We see that our function f of x minus L is less than epsilon is symmetric about C. How can we tell that? Is because since it approaches specific values, it's a constant. So if since it's a constant, here's our x values, this is our value k. Any value we take, it's symmetric about some point C. Likewise, this one. This is a linear equation. Any point we take, it's symmetric about some point C. We have equidistance. If it's one below, one higher. This one's also, since it has a finite limit, we see that they're symmetric. So we can find a delta that is half the distance from x to c. The problem is when it is not symmetric about c. We can take delta to be the distance from C to the intervals near endpoint. Let's see this. See when it is not symmetric. So if it's symmetric, just plug it in there, we'll get the answer. If it's not symmetric, we have to work it out. So here it is. How to find a delta for a given F, L, C, and epsilon greater than 0. We know that we have this. Delta. Step 1. Solve the inequality for f of x minus L is less than epsilon. To find an open interval AB that contains C. Where the inequality holds. All x not equal to C. Let me see. For all I can see, because we know that it does hold if x equals C. So now we're interested in if it's not equal to C. So we have to work out the f of x minus L part first. Second part. Find a value of delta greater than 0 in the open interval, which is AB, which is actually C minus delta, C plus delta. Centered at C inside the interval AB. So here we have A, here we have B. It's an open interval. So we have value C. This is C minus delta and C plus delta. Then the inequality f of x minus L is less than epsilon. Will hold for all x's not equal to C in the delta interval. Just for that, because since it is defined in the open interval, then we should go ahead and plug them in there. But since it's defined in the open interval AB, we have C inside AB. That means that C minus and C plus delta also have to hold. Example 4. For the limit of the square root of x minus 1 as x goes to 5 equals 2, find a delta greater than 0 that works for epsilon equals 1. That is, find a delta greater than 0 such that f of x minus L is less than 1. X minus 1 minus 2 is less than 1. Whenever 0 is less than x minus 5, this is the x minus c part. Solution comes down. Solve the inequality. In ours, it's x minus 1 minus 2 is less than 1. We do this to find the interval containing x equals 5, where the inequality holds for all x's not equal to 5. So we're looking for the c minus delta, c plus delta. We're looking for that interval. We'll get rid of the absolute values first. Add 2. So it's 1 x minus 1. Square each term. And add 1. So it's 2 less than x is less than 10. This tells us that the inequality holds for all x's in the open interval to 10. So it holds for all x's not equal to 5 in that interval. Second step. Find a delta to place the center interval into 5 minus delta, 5 plus delta. Centered at x equals 5. Inside 210. We see the distance from 5 to the nearest endpoint of our interval 210 is 3. Right. So we have x minus 5 is less than delta becomes this will place our x value between 2 and 10, giving whatever we have. And look at piecewise defined function. Prove that the limit as x approaches 2 of f of x equals 4 if f of x equals x squared when x does not equal 2 and 1 when x equals 2. So we see we have two proofs to the complete. Okay. We need to show that for given epsilon greater than 0, there exists a delta greater than 0 such that f of x minus L is less than epsilon whenever 0 x minus c is less than delta. So we have f of x minus 4 is less than epsilon when x minus 2. All right, so that's what we have to show. So solve the inequality f of x minus 4 is less than epsilon. We do this to find an open interval with x equals 2. Where the inequality holds for x not equal to 2. We see that x does not equal to c when equals to 2. We have f of x equals x squared. You need to solve x squared minus 4 is less than epsilon. X squared minus 4 is less than epsilon. Epsilon is x squared minus 4. So add 4. So we add 4 to both all sides. and square root everybody. This tells us that f of x minus 4 is less than epsilon, will hold for all x's not equal to 2 in the open interval negative x plus 4, epsilon plus 4. Now we have to find a value delta greater than 0. That places the centered interval, the internal interval of 2 minus delta and 2 plus delta inside the interval square root of 4 square root of epsilon plus 4. So do this. Take delta to be the distance 2 to the nearest endpoint of our interval. Nearest endpoint.